helicity and linking numbers. The topic and so as I was asked, we have to start with the definition. And plan of today is just to start with the definition using some not very well known, actually probably not so much known ways to interpret Biosavar, because Biosavar integral will play a role in the following discussion of helicity. And then I'll spend considerable time to just talk about concepts in topology, or if you want to be precise, low dimensional topology. I need this information, so there's not much to derive. It's a list of things that is useful to have with us in understanding the rest of this course. Okay, so I start with the definition. Definition of helicity, and I'll mention kinetic helicity. Remember, all these courses deals with basically fluid flows, classical aspects of vortex dynamics, and when it will be appropriate, I'll mention role of viscosity. For the moment, for today, no viscosity, Euler equations, okay? So this is kinetic helicity, H. Let's say at the beginning, consider it as a time-dependent quantity, and then we will soon discover that under Euler equation, this quantity will be conserved. But anyway, in general, H of t of, say, a fluid flow is defined by an integral h of t given by the integral of u velocity field dot omega in the volume of omega. Of course, if omega is 0, then evidently this is 0. Omega being, as usual, the curl of u, and the underlying quantities denote vectors. Okay, but we need to be a little bit more precise in this definition, and we take where V is, as I said, the volume, the domain of definition of vorticity. Better to say vorticity domain than bounded by a vortex, if you like, a vortex sheet, a vortex surface, such that so first of all, S, a vortex surface S, boundary of this V, such that there is no flux. We haven't any flux of vorticity through S. In other words, the vorticity omega dot, the unit normal pointing outwards, outwardly, the surface is 0. So in other words, this the boundary of the volume is a surface where the vortex lines are tangential everywhere to this surface. There is no flux through of vorticity. Okay, so this is the definition. And as I mentioned yesterday, Moreau, who passed away not long ago, well, maybe now 10 years ago, I don't know. For me, it's not long away. I met him in a celebrative meeting done on his birthday when he was already 80-something in Montpellier. Moreau, in 1961, published a paper where he showed that this quantity is conserved under Euler evolution. It is quite remarkable, so I take the moment to just stress that the number of conserved quantities of Euler equations the number is very small. Kinetic energy, now helicity, momenta, if you like, circulation. So maybe you have a chance to find another one. That's the challenge. And especially because we regard this one during this lecture under different light. And so it will reveal a different interpretation, unexpected, and that gives us hopes for possibly finding other conserved quantities. We never know. Okay, so this is the work of Moreau. As usual, when, as I said, noise or dust settles, then you can derive things quickly in one line or two. The original paper is a bit more elaborated. So the theorem by Moreau, let's say, is like this. For an ideal, in an ideal case, in ideal conditions, we take for simplicity, taking for simplicity of this proof, but not necessarily. But anyway, for simplicity, taking for simplicity the fluid density rho as constant, I'll set it as 1 for simplicity. Then in ideal conditions, kinetic helicity is conserved in time. Okay, so in order to prove this, so the statement basically say that the Lagrangian derivative of this h of t is 0, hence h is a constant in time. Okay, and the proof of this goes like this. I take the Lagrangian derivative of the definition u dot omega dv. I go inside the integral because I want to consider the surface as a material surface. So I get the integral of d dt u omega, and this evidently gives me the derivative of u dt omega plus u derivative with respect to time of omega. Right. Now you know how to do this, because du dt comes from Euler's equation, and d dt of omega, I wrote it yesterday as Lagrangian transport of vorticity, Helmholtz transport equation. So you plug in these equations, and you have v du dt is minus grad p omega, sorry, plus and then you have u, and then d omega dt is just omega dot grad applied to u. Okay. Say it again, please.
Is there any total derivative on the surface once we get the d by dt inside?
Yes, there is no contribution. Right. Okay, so you just have this. Now you have this grad operator, so you take it out, so to speak, and you have the integral of omega dot grad of what is left, minus p plus, well, we have a u and another u here, so we have a 1/2 of u squared in dv. But now we use also another fact, the fact that because omega is defined as a curl of u, we take the divergence of omega equal 0, by definition, if you like, and therefore we can convert this integral in the volume using divergence theorem to a surface integral. And so when we do this, we have the divergence of omega minus p plus 1/2 u squared, and is that correct? Yes. Sorry? Yeah, if you like, it's just getting to the on V. And this is, and this is, because there is a mistake in my notes as well. Minus p plus 1/2 u squared in ds, in omega ds. I put ds as a vector. Remember that, as usual, as we did yesterday, I take s with the vector notation as a normal s times the normal to the surface. And because the assumption is that we take omega dot nu equals 0, then evidently all this is 0, because we have this omega dot nu equals 0. So we have that this quantity is constant in time in ideal condition, and so we can explore its significance in a number of ways. The one way I'll talk about is, of course, its connection with the topology of fields. And in order to do this, I'll dwell on Biosavar first. So I'll consider Biosavar from two different viewpoints that help me to conclude something also quickly on the derivation of the linking number, and possibly, or later, its connection with helicity. Well, I like to say one thing, because I just mentioned its connection with the helicity. Good to remember that we have H, kinetic helicity, U dot omega dV is conserved in ideal condition, and we regard this as U dot curl of U in dV. Same thing. And then please just relax and think a field, not velocity field, any field times the curl of that field. Well, for example, if I think of MHD, then I can think of A as the potential for magnetic field, and the B dot curl of A curl of A being the doesn't look quite right. Is A equal the curl of B, or B equal the curl of A? Please. Oh, thank you very much. So you just swap these quantities. So we have A dot B. I go here. A dot B, right? Vector potential and the magnetic field in dV. And this is, I want to explicit it, A dot the curl of A. We take a Coulomb, typically, a Coulomb gauge, div A equals 0. Other gauges are possible. This is a good gauge. And you see the analogy that we have. We can call this quantity HM, if you like, and this is just a magnetic helicity. The other type of helicities, this is kinetic. My hesitation before to put this formula right was due to the fact that I can regard this or any field C times the curl of C as a product of a field times its curl. This was proven, not exactly the magnetic helicity, this type of integrals, let's say, this type of integrals, say C times the curl of C, any field, C, any field, any vector field. This was proven to be, this is an isotopy invariant of the domain of definition of C, if you like, curl of C, and this was proven by Whitehead. Remarkably, 1947. I just dare to make a terrible joke now. Why not? And, we have one world. You see, there is one world in which we live. And is simply connected, this world. But sometimes people put a barrier in this world. One of these, remember, these cut surfaces. And this is wrong, of course, because it's simply connected. And in this part of the world is DPMMS in Cambridge, Department of Pure Mathematics and Mathematical Statistics, I can't remember now. And this is the DAMTP, Department of Applied Mathematics and Theoretical Physics. And this barrier, now I'm very provocative because I'm in France, this barrier has two faces. I like to call this barrier Bourbaki barrier. And on this side is smiling, and on the other side is very sad. Whitehead was in Cambridge, on this side, and he showed this isotopy invariance in 47, and of course his formalism is not the one I'm using, because he used already differential forms and different language. If he ever encountered anybody on the other side, in the old times it was Silver Street, it was a simple way to communicate one another, would have been probably the case to have alerted somebody doing vector field in vortex dynamics or magnetic fields or whatever, that this was an isotopy invariant. In other words, yes, was conserved in 61 by Moreau, but it could be immediately interpreted in terms of topology. Okay, so sometimes these barriers are totally inappropriate, wrong. Right, okay. So this is the way it goes in terms of little history, etc. I ran into this paper when I was grad student in Cambridge, and I was very much embarrassed to tell this to Keith Moffat. He didn't know. He didn't know, and you understand what I mean by this emphatic statement. Okay, so we can, now we are, by the way, the conservation of magnetic helicity, not its interpretation in terms of topology, but it's the conservation of magnetic helicity in terms, in the context of ideal magnetohydrodynamics was done, why not, it's good to mention, by Volcher. Volcher, and actually earlier, 1958, in the States. So Moreau didn't know about Volcher. Okay, right. So we have this conserved quantity. We have a hint from Whitehead that has connections in topology, but we still don't know what we're talking about. So it's good now to say something about these ingredients. Well, these ingredients, okay, we have velocity and the vorticity, and remember the velocity is due to the vorticity, is the UR I used yesterday. So evidently, if U is due to vorticity, then this U can be thought of as Biosavar integral in terms of vorticity, okay? Because you just think, okay, U is given by Biosavar law, so it's a BS of U, of omega, so you substitute, you have everything, and a global integral of omega. Right, so I need to say something about Biosavar from an unusual, say, viewpoint, and I offer this interpretation. First of all, I like to give you an interpretation of Biosavar in terms of solid angle, because Biosavar is an induction law, and maybe you can be induced by the presence of vorticity by simply looking at the vorticity field. And when you look at the vorticity field from a point of view external of the vortex lines or the vortex tubes or whatever, you have a view of the vorticity distribution from a solid angle viewpoint. So the solid angle is a measure of this induction. It's very beautiful that the first entry, technical entry, to solid angle applied to fields, you have it from Maxwell. Maxwell. You go for solid angle, second volume, and you find the definition, etc., etc. And the remarkable way he not only happy to introduce the concept of solid angle, but he wants to work it out. He wants to make calculations. So he proposes 3 different ways to measure solid angles in practical terms that are still challenging people today. A paper on that came out maybe 8 years ago. Okay, so what we do is to show that in a simple situation we have this link, this connection between Biosavar and solid angle. So solid angle interpretation of Biosavar. That's the... Okay. So what we do, we consider, so in order to do this, consider I said, very simple case, consider a vortex line, say L, in R3, okay? And then if we consider a vortex, okay, instead of a line, maybe better to think of a thin, very thin vortex filament. So thin, not of 0 cross-section, so thin that we can neglect the cross-section, or we can consider it as a very thin tube, and we can integrate. Remember, Biosavar is a volume integral, so we can integrate over the cross-section. Being so small, we can take it out, this integration of omega through the cross-section, and that is called, of course, the flux of vorticity in the tube. So we have a u of x. The Biosavar integral I showed you yesterday reduces to gamma. Gamma is the circulation, so the flux of vorticity, so takes into account the integration across the thin cross-section. We have a 4 pi, and then the volume integral is reduced to a line integral. So we take a line of vorticity, and this is dl cross x minus x star. Remember my notation, x star is a point on the line of vorticity, and we usually have this green function inside. Right, okay, so now I'll do some elementary algebra here with you. Just, I want to go through this derivation with you, okay? So do step by step exactly what you would do in order to learn this. So I just change this dl, and then this cross product here becomes a cross product of the grad of 1 over x minus x star, and the grad operates on x. Okay, so I just swap this, and this becomes a gamma over 4 pi, and then because it operates on x, and dl is actually the elementary length on the vortex line, it does not depend on x star, it comes out. So I have the curl of the integral on L of dl x minus x star. And what else? Nothing else. I can call, let me call this quantity potential A, vector potential A, function of x. Okay, well, it would be x star as well, but you see I have a u of x here, and has to be, okay, I just like, I can put something like this. Of course, it depends also on x star. So we have a gamma over 4 pi curl of this A, right? Okay. So this is just manipulation. Now, further manipulations. Take a, how to say, a fixed vector in space and time, a fixed vector, I call it E maybe, unit vector fixed in space and time, and I want to work out the scalar from the vector A. So I define an AE, and this is given by A dot E unit vector, but because it does not depend on anything, it's just can be brought inside this integral. And so we have this x minus x star. Right, now what we do? Now it's, we can use here Stokes, and we have a line integral, and we can reduce it to the curl through L, and so the surface bounded by L, and so we have the integral of this curl operator. Now I put a star here because it refers to the x star points, and this is E over x minus x star well, all this in ds, and this I'll elaborate a little bit again, and this is ds cross just the grad star of x minus x star, and this is times E somewhere. Okay, right. So finally, I can write A I can write A of x as the curl on x points of what? Of this ds over x minus x star. And let me call this quantity w, another vector, okay? So this becomes the curl of this quantity w. Yes? Oh, it's just the operator on x star, because otherwise there is a minus sign. Right. Okay. Now we are almost done, because it's a matter to do some, to apply some vector identity equation to the expression that I have there. And so let me, I have very bad memory for these equalities, please excuse me. You see, with age it gets even worse. Anyway, curl of the curl of W, you know very well, you young, you know very well what is this. And we have the divergence here, and then we have minus the Laplace as usual. That was the source of the Poisson equation for vorticity. And this goes on like this. We have to replace the W, and so this is, okay, the integral over S of what? Of ds over x minus x star. And then we have to consider this as in terms of the fundamental solution to the Laplace equation. So here we will get a 4 pi integral of a Dirac delta x minus x star in ds. Okay, one more step is just to elaborate further from there. We have a minus and then x minus x star ds divided x minus x cubed, x star cubed, plus 4 pi integral delta x minus x star ds. And now, here, what we have. Remember, yesterday I couldn't resist to mention R is x minus x star, and I can introduce a R hat, a unit vector just given by x minus x star divided by x minus x star mod. And so I can reread this thing as, shall I do it? Minus grad, well, let me do it. Integral, I'm sorry, but I prefer you to see it in front of your eyes, what I mean. ds. Yesterday probably I made a mistake here. It was an omega dv, but of course you can reduce, well, it wasn't a mistake. You can reduce it to this. Oops, sorry, I got distracted. So we have an r squared, and I missed out somehow in my notes a 4 pi, but we leave it like this. We leave it like this. And if we consider, apart from the 4 pi, remember there is a 4 pi somewhere, and if you put a 4 pi here, you have a sphere. Okay, the sphere of the surface of the sphere radius r, and on top you have this product of a surface integral, or the surface element. So it's a pure number, and we call this quantity a solid angle, omega. Omega represents this. Okay, sometimes actually we will put a 4 pi here so that everything is clear. So evidently we will have a 1 over 4 pi there. And why this goes? This goes because, we consider the surface bounded by L. And the surface, well, think of a circle, of a loop, and this would be the surface, S, and this would be the loop, and this loop would represent the vortex line, and if it represents the vortex line, X star are the points on the vortex line. So the delta, Dirac delta, on these points is 0. Is 0 on the surface, okay, because evidently the definition of the Dirac delta function is that is 1, blah, 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 and when is 0 is 0. When the points, so when x is on the line, x star, etc., this goes to 1, otherwise this is 0. So that's why this is 0, because it is on this surface. Does not contain any point x star. Right. Okay, so this is... Again, Manuel may help me on the MHD side. Have you ever encountered this information in the MHD context? Okay, so this is not mine. It was posed as a problem. So you find this solution on internet, and it was posed as a problem, one of the problems in Jackson's book on classical electrodynamics. But we don't know why. I cannot say why. Okay, to some extent I'm not interested, but it's a little bit curious that it was posed as a problem. I think it was inspired by Maxwell, that's why. But it stopped there. Remember, for applications, probably also in Jackson's, maybe there was the idea to use a solid angle to compute induction of currents in that case. We don't know, but certainly I don't like to stop it here, and I want to go on by using this concept. Okay. So in order to do that, I'm proposing another exercise to you. Another little problem, and I'd like to leave it here, this part, or anyway, to interpret this. I'm sorry, I didn't finish. It's obvious what I had in mind. I said it in words, but I didn't write it. So when I go to you, evidently, this is, there was a minus from there, and there was a gamma over 4 pi inherited from the integrals above, and this is actually the final result. Sorry for that. I missed this part. I said it in words, so it was in my mind. I didn't write it down. So you have the velocity in terms of Biosavar, which is the velocity in terms of the solid angle, the grad of the solid angle. Okay. Now I can get rid of this. So I said, okay, I want to go on like this, see where I go. And if I go on like this with Biosavar only, I propose a problem. And I gave a little title to this section, Emergence. Emergence has more than one meaning. Anyway, in this case, well, I leave it. Emergence of appearance of topological linking. I'm not sure if emergence is the right word. It has the root, the Latin root is okay, but it gives the sense of something or something that is pressing. And no. I want to mean something that comes out from the formula. Okay, so for doing this, let's consider our vortex, the thin filament, and for the moment, I'll just think really in kind of pure mathematical terms, and let me think of something like this. So this is just a loop, a path that is embracing this vortex line. So this is my vortex line. Remember, there is vorticity here, but I can think of physics as well. It can be a line of velocity. Velocity. You know, if you look at the green line, I call it C. For me, it's a mathematical line, but you can think of a velocity line. And if you look at just the curve C and the curve L, you have your intuitive idea of linking between one closed loop, this one, and the other closed loop, this one. So for the moment, that's it. All right, so we want to calculate few things, and if I consider the surface, I hope to be correct here, S bounded by C. So let's say that, hope to be right. I'm just, my notes are a little bit messy on this point. Well, so C, I consider C as the boundary of this surface, and then I consider gamma, the flux of vorticity. Of course, you know what I mean, it's Stokes again. The flux of vorticity through this surface S. So this is just by definition the flux through S, and evidently this is curl of U in ds, and ultimately is just the integral over C of the velocity field. Okay, so we have UdL. Okay, UdL, fine. Now, well, that's okay. We could immediately plug in U with Biosavar and do our calculations. I want to be a little bit more, nothing big, just a little bit more sophisticated. And there are many ways to do this, and my way, I have no preference for one way or another. My way is this. For example, consider this not as is drawn, but for example, as making a number of loops. And oh, sorry, I'm terrible about drawings. Something like this, you see? It goes like this a number of times. And I'm assuming that it pierces this surface in single points, okay, isolated points. And suppose that these points, where it gets through the surface, let's say, let us consider the intersection of L with S in M isolated points. Okay. Right, so here we have 2. But it can be 3, 4, 5. If we have 3, it means that we go 3 times through this surface S. Okay, it's like a solenoid. Okay, we have here M points, M intersection points. For those of you who M intersection points, for those of you who did topology, you already know very well, because I use appropriately this word, intersection points. Okay. And, right, so what we do the following now. We have here, we have our omega ds, as usual, and this is, I repeat, the UdL, very well. But now I have M times the strength of this vortex line, because the vortex line goes m times through S. So I have m times gamma, if gamma denotes just the strength of this line. And it's time to recall again the Biosavar law, which is gamma over 4 pi integral dl cross x minus x star, etc., divided x minus x star cubed. Right. So I want to take this and plug it here, at this point. You see, if I plug it here, I have a relationship between m and the rest. So when I do this, I have omega ds as integral u dl. And now I plug it in the Biosavar formula, and I have first integral, this is c, right? And of course this is s. So I have the integral along c, and then the Biosavar formula here is along L, the line vortex, or the vortex line, sorry, and this is L. So dl, remember this is on x star, and then as usual, the stuff that you now saw many times, x minus x star. I have another dl. Remember that this dl is on x point, and this dl is on x star point. And okay, so this is it, x minus x star cubed. And now all this is m gamma. So we do this and we do this. So we have m now given in terms of 1 over 4 pi blah blah blah, the usual thing. And the usual thing is this m, well, I didn't say it, but I meant to say that m is takes values in n, so it's a natural number. It's the number of times that we have this L intersecting S. So this is an integer, is a pure number. This is a pure number, it comes from this. So in other words, this quantity is measuring the linkage between these two curves. So I can say this is m of L and C and L, these two curves together. And well, this quantity is exactly Lk, linking number. Lk of these two curves, C and L. Because ultimately we think of curves. And we use Biosavar, yes, true. But here is the connection that is missing in Jackson. The connection is, well, look, the velocity is given by this formula. And this formula comes from Biosavar. So we can think of this quantity here. I don't want to do it because I'm going to teach you a wrong way to operate. But you see, you interpret this as a grad of omega. So when you integrate the internal quantity, then you have integration in terms of omega. So in other words, let me leave it like that for the moment. I'll be back. But what I want to say is that the linking number can be interpreted in terms of solid angle. We have a solid angle interpretation of the linking number, and if you say this statement, there is no physics at all. If you plug in Biosavar and you talk about induction, you have the physics. But there's nothing new in Maxwell. In Maxwell, you have this correspondence between physical world and geometry. And so, I'm forcing a little bit in saying I'm using Biosavar, blah, blah, blah. But if I give you Biosavar strictly from potential theory, remember, from potential theory, I'm not mentioning any field. I'm just considering potentials associated with fields. Then I keep going, and I get to the solid angle. Any field. Right. Pardon me. I didn't understand. For M by sigma. What is sigma? No sigma. Right, okay, so we established a connection between, let's say, between this quantity, the solid angle, and, if you like, physics. Now, I'm almost done, actually, I'm done with these exercises, and I need to tell you really some things about basic information on linking numbers. I use the plural, linking numbers, because there are at least two different types of linking number. And as usual, I will mention, by the way, I just, instead of, I want to give you another, maybe you have interest in other fields other than vortex dynamics, or better, vortex dynamics from high energy physics viewpoint. And if you go to textbooks, of course, you find A wedge dA. Okay, A wedge dA is in Chern-Simons theory, and of course this is a potential, and is considered as part of the observables you have in Chern-Simons theory. And why I mention this? Well, of course, this is helicity, right? This is helicity in abelian condition. And I mention this now because I want you to remember that, of course, the helicity that we introduced, the kinetic, magnetic, etc., are also in Chern-Simons theory. And I was in Trinity in Cambridge, and at a certain point, one of the masters was Michael Attia, and Attia was obviously quick to tell Edwin, well, look, this means something, has to do with linking numbers, and maybe something else. So I will get back to this quick consideration at the end of my course, when I'll introduce not polynomials. And that led to the development by Edwin of topological quantum field theory. Okay. Right, so we have now the linking number, at least the way I introduce it here, and you take this as a definition of linking number. Now, it's interesting to say a few things about this. So Gauss is the author of this formula, and I tell you a few things about this because I did a piece of work on that long time ago. Topologists came to me, applied topologists, if you like to call them that way, came to me and say, Renzo, you have to explain how on earth Gauss got this right, because what he got right. He got right the following. I want to reverse, to go back to that M. In Gauss, this formula is written as 4 pi V. So there is a little note in his private notebook, unpublished at the time, 1833, where he mentioned two things. First entry, beautiful. He lamented the lack of progress in, let's say, topology, except Euler, van der Monde did very, very little things. He mentioned these two people. Euler, we know, with the Königsberg Bridge problem, and van der Monde. And he lamented the progress. Gauss was very fond of topology. He never worked on topology all his life. But remember, as I told you yesterday, be alerted the fact that Riemann got his chair, not because he was a student of Gauss, as many people say, not at all, because Gauss was chairing the selection committee. And he was, well aware of the quality of the work of this younger Riemann. By the way, bad notes to young people. If you're clever, you can do that. Remember, Riemann published only 11 papers in all his life. So no need to publish so much. Try to focus. This is after the PhD. Before the PhD, you have to work hard. But after the PhD, try to focus on, after permanent position, let's say. So that means when you're getting to retirement, you can relax. Okay, that's terrible. This is modern science. Anyway, so Gauss. And this is the entry. And then he gives this formula. No way to see where it comes. So evidently he got this result and he wanted to take note of this result. And then he says that this is, or if you like, V, is an integer, does not depend on the particular geometry, and this is a formula for two linked, we say now, closed curves in space. There is no physics. So when you read the people saying because he was working on electricity and magnetism, there is no proof of that. Actually, I prove the contrary. This formula is certainly related to his amazing work on geomagnetism. It's a long story, but anyway, I have a paper on that in Journal of Knot Theory, if you want to read it. But it's a very beautiful story, and he relies on the solid angle interpretation, because in defining the potential hypothetically induced by a magnetic shell, because he thought of the magnetic field due to the Earth, and so he thought of a hemisphere or a sphere inducing this potential. He worked out this solid angle interpretation of potential from scratch, from zero. You see, the first formula is so elementary. It's just induction due to the presence of something, and then he gets to the solid angle, and then he gets to this, and then he realizes that this is an integer and does not depend on the shape of this link. And the reason why it does not depend is a beautiful story. You can read it in my paper, because it's due to a number of observations done by Ampere and by others. Okay, but then this formula remained obscure, not known, unknown, until in 1867 was discovered in the middle of a bunch of papers, and most of these papers were on electricity and magnetism, and so they asked, actually, I think the chief editor of Nature at the time asked scientists a scientist in let's say in physics to put order in all this stuff. And so this paper, this one-page diary, was collected with the papers on electricity and magnetism. But remember, there is no mention of electricity and magnetism at all. From 1867, you see the date. Yesterday I mentioned the date 67 in Kelvin, and then his turn of Maxwell. So Maxwell, who could read fluently German, and as well as Tate, his schoolmate. Tate was the one who classified knots. I'll mention this because Kelvin asked Tate to tabulate knots, etc., etc. Tate could read German. He read Helmholtz. He gave a translation in English to Kelvin, but also Maxwell could read German. They were from Scotland, and that was the schooling. And when Maxwell looked at recent publications got from available in the Cambridge University Library, he immediately sent a postcard. At that time, it was very expensive to send mail, so these postcards I've seen with my eyes, they were very little like this, you know, like what we use, the people never could achieve such a level, but the people, important people, they show you the card they have for. Anyway, and on, of course, on one side you had the address, on the other side something. And on this something, Maxwell was always amazing, putting many information in just hints and lines. And one of them says, I just found in CUL, Cambridge University Library, this collection 67 in 67 of Gauss papers. And so he rushed immediately to try to demonstrate this formula. So the formula has a demonstration in terms of solid angle that was not given by Gauss, but is given by Maxwell and is in his second volume of Electricity and Magnetism. Very, very amazing. Not only because he derives this formula, he says to Tate, he says, well, this formula has no derivation, but is good to have it. So he derives the formula. He duels on solid angle definitions and how to work out solid angles in applications, and goes farther. He says, well, this formula has some limitations. I'm not going to tell you which ones, we wait, but evidently has to do with not polynomials. Of course, Maxwell didn't talk about not polynomials. He said it has some limitations. The linking number formula of Gauss has some limitations. You can conclude if there is any link, between helicity and linking number. If linking number has limitation, helicity has limitations. Okay, so this is the story. This is the formula. There's nothing else I can do. It's just this, and you can read it out in terms of solid angle because of this 4 pi blah blah blah. Now this V for Europeans, or at least people who grew up with this science in Europe, this V speaks books. And for an American educated person, maybe doesn't say much, but for us it means potential. So simple. Is potential. No question about that. So that was the hint I got when I saw this capital V. He doesn't mention anything, okay? But then in his derivation of the geomagnetism is a long paper, 60 pages. Of course, it deals with this. Right, so what I have to say about this formula? Well, so this is the linking number formula. If you evidently saw the connection between a vortex line and the induced velocity, so it's a linkage. Is a linkage between vortex lines and the velocity. What is the connection with helicity? We have to wait a little bit more because I want now to focus on this information. Okay, so we have a linking number now coming up, and I just use this word as a kind of a theorem, and theorem goes like this. The linking, of course, is not written anywhere, it's just my wording. The linking number LK, 1, 2, meaning LK of a curve, say L1 with L2, just forget about the vorticity and velocity or an abstract, so just two curves for the moment, is a topological, we didn't prove it, but you can prove that is a topological invariant of the link as I showed you. For example, a two-component link, I will denote the link as a disjoint union of two closed curves. And this is the first statement. I mean, this statement without proof is in Gauss. In a Gauss note. This is a pure number, is a topological. quantity, and LK 1, 2 takes values in Z, because there we had the vortex line piercing the surface in one way, assuming that the boundary of the surface was also oriented, if you think of that as a velocity line. But then it depends on the mutual orientation. If I pierce it one way, I have a plus. If I pierce it the opposite way, I have a minus. So this is why I go from N to Z. And then another story is that, as Maxwell says, L1, L2 is equal to the linking number of L2 and L1, no preference in the order. So it's a symmetric. Well, you see it here. You see it here. It's evident. You can swap X and X star, and you get this. So there are three properties. This, and the fact that it is a topological quantity. Now, probably good idea to stop here briefly, and I'll continue. My aim is to tell you something that has a more than a sense, that has a more than a flavor. I mean, that has applications. Okay, because this, sometimes we look at mathematicians as very clever people. I saw papers trying to prove that this is invariant by integrating geometrically on loops. But it doesn't make sense. If you deform slightly whatever geometry you take, how can you keep going with this? It's really terrible. Must be a more clever way. It's a topological quantity. It does not depend on geometry. So there is no point to, set on your Mathematica program a circle linking with another circle, computing this, okay, but then deform these circles. How do you do this? I mean, it's a bad line integral to compute. It doesn't make sense. Okay, we stop here, and I give you techniques to compute this linking number in all possible crazy situations. And then I will consider another linking number, which is the limiting form of this quantity, which is called the self-linking in modern times. Okay, I stop for a few minutes so we can stretch our legs. Now we just defined, so to speak, the linking number, and through a number of well, there are many ways to prove that is a topological invariant of links. What is a link is just, is a closed curve in space, and is a multi-component of several curves, closed curves, one another, linked in space, and typically we use, or I use these L for a closed curve, a disjoint union of another curve, for example, but you may have 3 curves, 4 curves linked together. So this is a link of 2 curves, so of 2 loops. So this is represents a 2-component link. Because I know that some of you have maybe problems to understand what I mean. This is the link in space in R3. I mean one closed curve that goes through the other like this, and say L1 and L2, and the business is that there is no way to reduce this to 2 disjoint components that are unlinked. No way through a diffeomorphism. You have to somehow cut it cut the link somewhere through and then separate these things. But if you do not cut these things, the link stays like this forever. You can deform it, and of course deformation involves change of geometry but not of topology. On the other hand, I talked about a knot. A knot is, well, I'm forcing a little bit the language, is one component link, and that is a knot, okay? A knot, knot in space, not say K. I'll use very often any one of the two to mean what is obvious. For example, this is the trefoil knot, okay, and this one single curve in space, and it cannot be reduced through diffeomorphism to a, this loop is very often called the unknot, okay? So it's not homeomorphic to the unknot. And right, so links, you may have multi-components for the link, for a link, and knots, well, we have, you see crossings here, maybe 3 crossings. If you go to, the number of components evidently is a topological quantity, is just defined as 3, 4, 5, 6 loops together, linked together, inseparable one another. Knot is just one component. From the planar projection, of these loops, you go to the minimal number of crossings. Because you may have a crossing that is like this, okay? That is like this. This is an apparent crossing. Apparent crossing is a loop that can be deformed continuously to just this, to an arc. If you can, you go to a diagram projection, you take a knot or a link in space, you have your preferred knot, just for simplicity, think of the trefoil knot. You project it along a projection onto a plane, and you get a diagram, okay? A diagram. This diagram of this knot, you may call it, say, K0, but not necessarily it has a minimum number of crossings. It may have a curly bit like this, so you count the crossings, 1, 2, 3, and 4. These are the apparent crossings. But you want to go in the diagram projection to the minimum number of these crossings. And you may try to modify the geometry of this projection, or you can take different projection directions, different planes, and maybe on one projection, this curly bit disappears. Maybe you see it from this side and you don't have it anymore. Okay? So the minimum number, so we have the number of components, of course, is number of components is an obvious candidate for a topological quantity, but also the minimum number of, I want to say of apparent crossings. Why I say apparent crossings? Loosely speaking, people talk about crossings, but in our case, here, we like to say apparent crossings because a crossing, technically, is what Louis avoided in analysis, a self-intersection of the curve. Okay, a self-intersection of a curve. So we do not have self-intersections. And the idea to represent apparent crossings in this fashion by interrupting the diagram and showing up the overpasses and the underpasses is just the visual representation of topology on a diagram. Well, something obvious, you know, is so intuitive, but it took 15 years to Tate to realize that. he used to, he used to denote a crossing like this, and then he had to put dots to denote if it was overcrossing and undercrossing. If you check on his first tables of knots, it's a terrible thing. By the way, 2 dots were representing a coin of silver and another one of copper. And that was his way to denote overpasses or underpasses. And it's amazing, something so obvious. Now I can't remember what it was. It was like this. It's amazing to think that it took so much to him to realize this. It's so intuitive. Anyway, we have apparent crossings. If we go to the minimum number of apparent crossings, in that case, we have a topological quantity. So the trefoil knot has 3 crossings, the 4-crossing knot, has a 4 crossing, the 5 crossing, and so on. We have knots of increasing minimum number of crossings. But, well, it's a long story now, because if you go to the mathematical classification subjects of maybe 15 years ago, I remember that there was almost no entry for low-dimensional topology and physical knot theory, and now there is a section with the subsections devoted. Just to give you an idea of the work that was done from the 70s onwards, when Conway made a very important contribution to the field, etc., etc. So we have, well, maybe this is trivial, this is also pretty simple. We have a number of quantities that have a topological character. In the case of a link, we have a linking number, Gauss linking number, Gauss linking number. Now we'll see how it works in practice. Let me say one more thing about this. We like, because we deal with vector field lines, we like to orient these curves, these loops, okay? Something like this, for example, something like this. And what we mean is very clear to all of us. We mean, for example, a vortex line or a current line, something like this. So the orientation on knots and links comes because we have orientations from the vector fields. And we like to deal with oriented knots and links. So there is, you see, a kind of specialization in knot theory in dealing with oriented knots and links. Now, I can talk about the linking number when the linking number is referred to, say, 1 and 2 curves or other curves. I call this quantity LK12, and that's fine. I can compute this quantity because evidently, if I go on a computer and I want to compute this quantity, what I have to do is to prescribe in a computer the geometry of these lines and integrate on double integration along these lines, which is very expensive and terribly bad. But of course, if these lines move in space and the link is not destroyed, there is no change in the topology, then I have to recompute all these all the times. Still very expensive. Computation of Biosavar, which is hidden there, is terrible. Now, you saw that the linking number came, the little m, came from intersections of one line with a surface. And if you think of this surface, you remember the surface had a boundary, and at a certain point I said, okay, for me it's a mathematical loop. But why not thinking of that line as a velocity line that is indeed related to the vorticity of the filament? And if it is a line like that, then I can think of the surface spanned by the boundary, or the other way around, and the line bounding the surface, and the surface has a name. Not only in that particular case of a simple loop, but in a very complicated case, for example, like a trefoil or any knot you like and link, you can always think of a surface that has boundary, this link or this knot, and these are called Seifert surface. And if you use the concept of Seifert surfaces, Cipher surfaces are not surfaces, are particular surfaces whose boundary is a link or a knot, but these surfaces are orientable. So of the infinitely many surfaces, you take the orientable ones, and any orientable one, still many, many. Think of the circle, the circle. How many surfaces have? You have this one, of course, is the disk, but then you have also the hemisphere that is bounded by this line, or any other big, you have many, many of these surfaces. Think of the potential. Think of the potential. Okay, potential surfaces. Anyway, these surfaces are called Seifert surfaces because they are orientable, like a planar disk. Like a planar disk has a north side and a south side. Now, if you consider a curve that goes through this surface at a single point, here, whatever, then you have another interpretation of the linking number in terms of intersection numbers. Intersection numbers. Of course, is related also to solid angle. But you have a very applied way to define the linking number, something that we will like a lot. And we have to consider, first of all, oriented loops. Now, these represent my diagram, my projected loops on a diagram, this one, the blackboard. And then I assume that I got rid of all the coils, the extra crossings that are not changing the topology. For example, anything that does like this, apparent crossing here, can be reduced to something like this. This is a well-known move, is called Riedmaster type 1 move, R1. And you can get rid of these coils like this. And then there are other moves, R2 and R3, introduced in the 1920s. And according to these moves, whatever you have as a projected curve with its apparent crossings, then you perform these moves and you can reduce let's say complexity, the apparent crossings. When you get to the minimum number of crossings, don't ask me how, I mean by trial and error. Tate did that in the evenings. Put a cord on the floor and try to move one way and another, and he tabulated hundreds of different knot types. Now, when you do this, of course you can do it with a computer, it's the game of the 30s, then you can classify knots. Now, if you put orientation, you have something else. Well, for example, we like to introduce a convention, and the convention is very simple, is this sign convention. And this is the convention. We have a strand and an underpasses, apparent crossing. I'm looking at one of the apparent crossings in the diagram. For example, here, or here, or here, or here, or here. And then I tell you how to do it. You use your thumb, right hand, you put whatever strand you like. I usually pick the overpasses, and then I look. If it is consistent with my fingers direction, then it's a plus. Otherwise, it's a minus. So in this case, it's a minus. I can say -1. And then I can do the other way around. I can say, okay, I leave this and this, just for fun. And then I put my thumb on the overpasses, and I see that is consistent with the direction of my right-hand fingers. So I say that this is +1. Okay? So I have a way to compute, to associate to each apparent crossing an algebraic number. +1, -1, according to orientation. Now, I made up these loops without thinking, so let's use them as an exercise. So I go like this, and the underpasses goes in this direction. So this is a plus, correct me if I'm wrong. And what about this? You have to put your arrows, and then like this, so this is a plus. So I have 1 plus and 1 plus, okay? And what about the trefoil knot? Well, the trefoil knot is not a link. And I'm saying that I have a Gauss linking number. So this quantity is just reserved for links. However, I introduce a convention. I can use the convention to compute whatever is the plus or minuses that appear here. So I have, for example, you put your arrows, you follow, arrows, you follow, you follow, you follow the line everywhere so that you can identify this as a minus, and you go here is another minus, and you go here is another minus. You have 3 minus. Okay, if you reflect this into a mirror, you have a mirror image of this trefoil knot, and you get 3 pluses. So the trefoil knot has a mirror image with the opposite, of course, signs. Okay. Now let's go back to linking number. The good news is that we can compute the linking number through these signs. So what you do, you have your very complicated link in space. You project it. Imagine in a computer, you have a very complicated pattern of lines, and you project them. And then you say, but I have to look at the best projection, the one that gives me the minimum number of crossings. No. Why not? Because the linking number is a topological quantity. It does not depend on projections at all. So you can compute the linking number, LK, LK12, as it's a formula. You take it, please, because otherwise to derive this formula is easy, not difficult. Maybe in the notes you have it, but it's a waste of time here. So you have 1/2 of the sum over the apparent crossings, epsilon, I'm sorry, I'm using R again, R, where epsilon R is plus or minus 1 in your computation of the signs, and R takes values in the intersection. In this case, we have only L1 and L2, as L1 intersecting disjointly L2. Okay? So in practice, I go here. How many R I have? I have L1 intersecting L2 in 2 places here. Remember, if I have something like this, okay, an apparent intersection of L whatever 2 with itself, it doesn't count, because this is reserved for L1 intersecting L2. So this does not matter at all. And then I count this. This is a +2. So if it is a +2, I go inside here. I have 1/2 of the sum of +1, +1, +1, +1. And so this is exactly the linking number of my Hopf link. That is called Hopf link. So in other words, instead of calculating this thing that is terrible, computationally expensive and very, imagine that is a time evolution of the loop or the link, etc., is terribly expensive, then because it's topology talking, you take at any time you like a projection, and then you tell the computer, you write a piece of code that encodes this information. And so this is a +1, the linking number of Hopf link. Well, you can do a number of examples, so I have to resort to my diagrams here and the notes, because I'm terrible about improvising these diagrams. Some of the knot theorists are extremely good, but some are also pretty bad, and I'm not a knot theorist, so I can be very, very bad. Right, so let me say, okay, suppose we have, be patient, something like this, and then changing color, something like this. I'm doing something simple, don't worry. Something like this, and imagine that we are already with the minimum number of crossings apparent in this diagram. If it is not the minimum number, don't worry, doesn't matter, because what you get is anyway a topological quantity. For example, if this green line goes over, oh, we can do it. We can do it later. So, okay, let me orient this, for example, like this, and for example, like this. Okay, and then I want to compute this. So I give my computer this rule, and this is a positive. Please pay attention because I made mistakes. So this is a positive, this is a positive, and this is a positive. So this, the linking number of these two loops is equal to 4, 2. Okay? Okay, so this is positive. This, I'm looking at the overpasses, is positive. This is positive, and this is positive, yes. There are four pluses. So you see, this formula for the linking number is, well, I do one more example of this, but we can forget about this. Oh, so easy, so easy. You instruct your code to take projections, good projections. Sometimes you have an overlap of these lines. You don't want to, so you perturb a little bit your projection so that you can distinguish and to have, in order to have well-defined apparent crossings. And then you instruct your computer to count the plus and the minuses, and you do the summation, and you get the linking number, right? So I do one more example. So this would be evidently linking number of, say, two curves, L1, L2. Right. Let's do another example here. Another example can be this one. Okay, we have the figure of 8 naught. Oh, yes, why not? This, I used to do it in a vertical way, but it doesn't matter. This, and then we have another one, which is this, going under, and this. Okay, now we orient it. I'm just improvising an orientation like this, this, this. We put orientation as well here, 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 goes like this, here. Now, pay attention. Here we have an apparent self-intersection, an apparent crossing between one strand of, say, L1 and the other strand of L1. And so that doesn't count towards linking number. And then I do my little work here. Is a plus, and here is a minus, and here is a minus, and here is a plus. This is called Whitehead link. It's a special link. Oh, what a pity. I was so happy about this linking number of Gauss that now what I find that the linking number of this is 0. But the linking number of this unlink is also 0. So when I was your age, I went to a conference and they communicated that what topologists call linking number by Whitehead, the Whitehead link, should be called Whitehead Maxwell link. Why Maxwell link? Because again, you go to the second volume of his Electricity and Magnetism, and depending on the editions, say page 72, you have it. He derives the Gauss linking number. He talks very much highly about this great number, and almost immediately he shows that this contradicts the power of this linking number, because linking number is supposed to pick the topology. But in this case, it's evidently not doing that. The linking number of the trivial link, the unlink, and the linking number of the figure of 8 link is, or the Whitehead link. So this is figure of 8, figure of 8, sometimes referred to as a Whitehead link, should be called the Maxwell link. And 1, 2, 3, 4, and there is one more, okay? So this is a 5 crossing link. Okay, now in a letter to Tate, of course Tate was very disappointed by this. His friend, his good friend Maxwell, communicated this news to Tate, and Tate was, you know, there are, as we do in our work in topology, there are the ups and downs, the moments of the classification of knots. So it is called the blues of topologists. And so he had immediately one blue period, because he was thinking that linking number was capturing topology in a great way, but then Maxwell alerted him that there are instances in which linking number fail to detect topology. For example, I can take this linking number, and of course 3 unlinked loops, and evidently this is 0, because remember, we go for the minimum. In the older times they went for the minimum number of projections, etc., etc. But what about this, that you may guess what is? The way I learned to do this is first to consider three loops, one on top of the other, and then one on top of this one here. This on top of the other one, so going over here and going over here. And this on top of this one, so it's going over here, and is going over there. Now, if I emphasize this, I have one loop that is linked, so to speak, because it's actually every single pair is unlinked with the other. Sorry. Okay. So I don't know if you can see this well. I put some arrows here and here, arrows here and here. Any orientation you like. And what about this one? Like this, going this way. Okay, like this way. These are called the Borromean rings. Borromean rings, because they come from the coat of arms of the family near Milan, of the Borromea family. Borromea was a famous family. There's a long story. There's a beautiful article by a lady. Please forgive me, I can't remember the author, but it's not so hard to find the paper on history of these Borromean rings and why they became a symbol of the family. But if you pay attention to, for example, this one, and this one, and you, in your mind, you remove the white one, you see that the orange and the green are unlinked. And you do the same, remove the orange, and then you see that the green and the white loops are unlinked. So each pair is unlinked, but the 3 together are linked. Point is that let's compute the linking number of this thing. Okay, so we have to do our work on arrows. So here we have a plus. Please pay attention because I may make mistakes. There's a plus, and here, let me see. This is a plus, and there is something wrong here. I am sure. Going on top of the white goes on top of the orange, and the orange goes on top of this. I'm not quite sure if it is correct. Let me go on. Let's see. So this appears to be a minus. I'm surprised. Okay. Okay, so this is a plus, and this is a minus. And this is another minus. 3 pluses and 3 minuses. Computation is okay, but my way to see this is different. Anyway, so linking number 0 in this case as well. Oh, another blow. Oh, so linking number is not enough. We need something more, because evidently this and this are different objects. So I'll move on, leaving with you, leaving the idea that is not enough. It would suffice this to convince you that we need more information to capture different topologies. And this more information is what has pushed people to look for other invariants. So we are, I mentioned Ryder Master moves in 1920s. I mentioned Conway, 1970. We had to wait a long time, almost 100 years, from the Tate tabulation of 1870, more or less, went on till the 80s. Tate, 20 years, the blues of a no theorist, up and down, very happy and then very sad again, and then very happy again. And we have two problems. One, linking number is not enough, because you see simple links, as simple as 4 crossings, 5 crossings, we have already a problem. Linking number is not capturing, distinguishing this from the unlink. And the other problem that in disguise I left it here for you is that we don't have any information for a knot. That is Gauss linking number, measures link topology, but not knot topology. So I'll freeze the situation here, because I want to go on, if I can, just maybe a few minutes, just few minutes. And I want to be very, very quick in introducing you a measure for a knot. So what about a knot? Well, I have my way, my 2 minutes way to introduce a knot. I cannot be precise, 2 minutes. The paper I have in mind, or the man who developed this, is a Romanian man. He wrote 2 papers, and the relevant one is 1961, is a differential geometer from Cluj. And by the way, his son is also a professor in differential geometry, the same name, Calogeriano, still there. And when I was your age, I discovered the work of Calogeriano that went lost, completely lost. So the problem is the following: what about measuring self, of course, is self-linking. A knot, does it have a kind of self-linking information? So my 2 minutes way to introduce this is the following. I start with the well-defined quantity, which is the linking number. So I take something like this, okay? Is a well-defined thing. You want to put orientation, very well, we do it like this. So this is a linking number of Gauss. Well-defined, right? So we have an L1, an L2, everything is fine. And this LK is perfectly well-defined, LK of L1 and L2. Very well. Now, do this with me. It's not exactly the way Calogeriano did it in mathematics, but it's okay in 2 minutes. It's again a long paper in French. Okay, and keep this L2 fixed, rigid, is a piece of wire, okay, L2. And then you take this one and you deform it. You deform it as a piece of cord, and you deform it so that it goes all the way, very close, running parallelly to this green wire, right? And then, okay, you want a little bit of mathematics, why not? So we call L, I started with L2, okay, I keep going. L2 is defined by a curve, x of S as arc length, x is just the vector position, and then L1, if you, sorry, what I did here. L1 is, I construct L1 from L2, going along L2 as close as possible. So I define, this is x1, I define an x2 in the following way. I take x of s as a basic curve, and then I move it away, an epsilon away, and then along some direction, a normal vector field, and not necessarily the principal normal or the binormal, any normal, say u. Okay, so epsilon is the ribbon width, and I define the mathematical ribbon R as given by these curves, L1 and L2. And then, hand-waving demonstration of 10 seconds, I take the linking number, I take the limit lim of epsilon going to 0 of the well-defined LK of L1 and L2. Here there is an epsilon, because when I connect these two together, I have an epsilon. And when I take the limit, this is a well-defined quantity, it's a topological quantity, and amazingly, I can prove, or Calogero proved, that what you get is also a topological quantity. And let me explicit it, and then next lecture I'll be more precise. This I call the self-linking. I have to warn you on this, just a little note. Probably is not in my notes, or I will put it. Mathematically speaking, self-linking number was mentioned or defined in a different way by an American mathematician, Paul, but in the 70s. But I prefer to use self-linking for the limiting form of the Gauss linking number in this situation, because it gives you the idea that is a kind of a linkage between one of the neighboring curves. Remember, we deal at the end of the day with the tube of vortex lines. So say one of these vortex line linked with the center line of this tube through this ribbon definition. Okay, so the ribbon is something like this. Imagine that this is starting to draw here and to draw here, and this is the unit vector u. The if you wish, the width or half of the width is epsilon, doesn't matter. And then this is self-linking of what? Of L1 and L2. But now L1 and L2 are one object. So I call it self-linking of the ribbon. Okay, better to stop here. Self-linking of the ribbon. Can you speak up a little bit? U is a unit vector. Unit vector. Unit length vector. And any unit vector. If you're happy about the binormal, okay, the binormal, not necessarily. It depends, of course, on the choice, but not at the end result. And so we have the self-linking of the mathematical ribbon that basically defines your tube. So you have to frame the tube. You have a tube of a vortex line, and then you have to put a framing. The framing is due to this u. According to the choice of u, you have a framing, you can compute this quantity. I will tell you in the next lecture how to compute this quantity, because of course it involves the geometry of the, why not? I can say that this is a remarkable formula. this says that this quantity is a topological quantity, can be decomposed in two global geometric quantities. One is called the writhe of the center line here, let me say L at this point, plus another quantity which is called the twist or total twist number that depends on the ribbon. And these are global geometric quantities. And this is topological. Is a remarkable formula. We have maybe 3 entries, or maybe 4, in the all mathematics that relate topology to global geometry. Milnor, some very few results, Gauss-Bonnet, Euler characteristics and total curvature, etc. So very, very few. So this is one of them. Topology, you can decompose somehow topology in terms of global geometric quantities. We will talk about that. And of course, relation with helicity. Thank you.